Organometallic Chemistry by Arso Shariar. Here are the table of contents. Hello everyone, welcome back to another exciting vlog. In today's video, we're diving into an intriguing and educational topic, organometallic chemistry. Before we get started, don't forget to like, subscribe, and drop your thoughts in the comments below, and of course, hit that bell icon to stay updated on all future content. So sit back, relax, and get ready to explore this fascinating subject. Let's get started. Welcome to the vlog. You may be wondering, what is organometallic chemistry? Organometallic chemistry is the study of compounds that contain a bond between a carbon atom and a metal atom. The field has a long history with important discoveries dating back to the 1700s. Here are some of the early discoveries. In 1760, Louis Claude Cadet de Gascourt isolates cacodiol, the first organometallic compound. In 1827, William Christopher Zeiss produces Zeiss's salt, the first platinum/olefin complex. In 1848, Edward Franklin discovers diethyl zinc, and lastly, in 1890, Ludwig Mohn discovers nickel carbonyl. Now, here are some of the classifications of the organometallic compound. Organometallic compounds can be categorized based on various factors. Type of metal involved, main group metals, transition metals, lanthanides, and actinides. Type of bonds between metal and carbon, ionic bonds, covalent bonds, and pi-bonded interactions. Hapticity of the legion refers to how many carbon atoms are directly attached to the metal. Molecular structure: mononuclear, which means single metal center; binuclear, two metal centers; nuclear, multiple metal centers. And then some of the common classifications. So main group organometallics, transition metal organometallics, ionic bonded compounds, sigma bonded compounds, pi bonded compounds, and multi-center bonded compounds. Now, here are some of the industrial applications of organometallic chemistry. Organometallic chemistry is vital across industries, enabling reactions difficult for conventional organic chemistry. Polymer production. Organometallic catalysts like Ziegler-Natta improve the efficiency and cost effectiveness of producing plastics such as polyethylene and polypropylene. Pharmaceuticals. Organometallic compounds aid drug synthesis with organopalladium catalysts, facilitating cross-coupling reactions. Example, Suzuki Heck, to create complex molecules and APIs. Petrochemicals. Organometallic catalysts are essential in oil refining and fuel production, with Fischer-Tropsch synthesis converting CO and HO into hydrocarbons. Green chemistry. These catalysts enable energy-efficient, low-waste reactions supporting sustainable chemical processes. Fine chemicals and agrochemicals. Organometallic chemistry is key in making herbicides, pesticides, dyes, and fragrances, with Grignard reagents playing a major role in fine chemical synthesis. Now, you may be wondering, what is hapticity in organometallic chemistry? Hapticity in organometallic chemistry refers to the number of atoms in a legion that directly bond to a metal center. It is denoted by eta, followed by a number indicating the attachment points. For instance, eta 1 means one atom is bonded, while eta 2 involves two. Higher hapticity, like eta 5 in cyclopentadienyl legions of ferrocene, shows multiple atoms forming delocalized bonds with the metal, This concept is key to understanding Legion metal interactions influencing the stability and reactivity of organometallic compounds. Now, you may also wonder, what role does hapticity play in organometallic compounds? Hapticity in organometallic compounds refers to the number of Legion atoms directly bonded to a metal center, influencing structure, stability, and reactivity. Higher hapticity increases electronic and steric stabilization, as seen in ETA 5. Cyclopentadienyl complexes, where all 5 carbon atoms contribute to bonding. Lower hapticity, like ETA 1, involves single atom bonding, while ETA 2 allows TT complex formation, as in alkenes. Even higher values, such as ETA 6, benzene, and ETA 7, rare sandwich complexes, showcase extended TT system interactions. Controlling hapticity is crucial in catalyst designs. Pharmaceuticals and advanced materials optimizing reactivity for industrial applications like catalysis and polymerization. Now, you may be wondering, defining the 18 electron rule in organometallic chemistry. The 18 electron rule states that transition metal complexes are most stable when the central metal atom has 18 valence electrons, combining its d electrons with those donated by legions. This fully fills the metal's 9 valence orbitals, mimicking no gas stability. Legions contribute electrons via sigma or pi bonding to help achieve this count. Stable complexes like ferrocene and metal carbonyls follow this rule, while 16 electron complexes, such as Wilkinson's catalyst, tend to be more reactive and useful in catalysis. Though exceptions exist, the rule aids in understanding and designing organometallic compounds for catalysis, synthesis, and materials science. The 18 electron rule in organometallic chemistry explains the stability of transition metal complexes, stating that a metal is most stable when it has 18 valence electrons. Similar to the octet rule, for main group elements, transition metals have 9 valence orbitals, allowing a maximum of 18 electrons for a noble gas-like configuration. Legions help achieve this by donating electrons through sigma and pi bonding. Stable complexes like FeCO5 and ferrocene follow this rule, while 16 or 17 electron complexes such as Wilkinson's catalyst are more reactive and involved in catalysis. Though not absolute, the rule is a key tool in predicting stability and reactivity in organometallic chemistry. Homogeneous catalysis, a key application of organometallic chemistry, involves catalysts dissolved in the same phase as reactants. Typically in a liquid, this allows for efficient, selective, and controlled reactions widely used in industry and laboratories. Common examples include hydrogenation, hydroformylation, and carbon-carbon coupling. Example, Suzuki and Heck reactions. Organometallic catalysts facilitate these reactions by coordinating with substrates, weakening bonds, and lowering activation energy, while homogeneous catalysis offers high selectivity and precise control. Separating the catalyst can be challenging. Despite this, it is crucial in pharmaceuticals, fine chemicals, polymers, and green chemistry, with ongoing advancements, improvements, stability, recyclability, and efficiency. Heterogeneous catalysis, a key process in organometallic chemistry, uses a solid catalyst to facilitate reactions with gaseous or liquid reactions. Unlike homogeneous catalysis, it allows for easy catalyst separation and reuse, making it cost effective and sustainable for large scale production. The process relies on adsorption, where reactants bind to the catalyst surface, weakening bonds and enabling new ones to form. Metal nanoparticles on support materials, example silica, alumina, enhance efficiency by increasing surface area and active sites. This method is widely used in petroleum refining, hydrogenation, catalytic converters, and ammonia synthesis. Advances in nanotechnology continue to improve catalyst performance and sustainability. Now, you may be also wondering, what are Grignard regions in organometallic chemistry? Grignard regions are highly reactive magnesium compounds, essential for organic synthesis, especially in forming carbon-carbon bonds. Discovered by Victor Grignard, the act is as strong nucleophiles reacting with carbonyl compounds to produce alcohols. Due to their moisture sensitivity, they must be prepared under dry conditions, typically in either solvents, widely used in pharmaceuticals, agrochemicals, and polymer synthesis. They enable the creation of complex molecules. Industrially, they help produce fine chemicals, drug intermediates, and advanced materials. Despite their reactivity, careful handling is required to prevent degradation. Ongoing research continues to expand their applications in organic chemistry. Now, you may wonder, how are Grignard regions used in organometallic chemistry? Grignard regions are highly reactive organometallic compounds used in organic synthesis to form carbon-carbon bonds. Acting as strong nucleophiles, they attack electrophilic carbons, especially in carbonyl groups, to create alcohols and complex molecules. Their versatility makes them essential in pharmaceuticals, fragrance synthesis, and polymer production, supporting various industrial and scientific applications. Transmetallation in organometallic chemistry is a transfer of an organic group or legion from one metal to another, effectively swapping metal centers between compounds. This process is crucial in catalytic cross-coupling reactions like Suzuki, Negishi, and Still couplings, enabling the formation of new organometallic complexes. The Ziegler-Natta catalyst is an organometallic compound that enables the polymerization of alkenes into high molecular weight polymers like polyethylene and polypropylene. The process involves the alkyne binding to the catalyst, its insertion into the metal carbon bond, and the continuous growth of the polymer chain, with the catalyst being regenerated for further reactions. This catalyst is essential in producing plastics with controlled structures and properties, making it widely used in the polymer industry. Organometallic chemistry plays a vital role in modern science, bridging the gap between organic and inorganic chemistry. Its compounds such as Grignard reagents and Ziegler-Natta catalysts are essential for synthesizing complex molecules, forming carbon-carbon bonds, and producing high-performance polymers. Reactions like transmetallation drive key industrial processes, enabling advancements in pharmaceuticals, materials science, and catalysis. As research continues, organometallic chemistry will remain crucial in developing innovative solutions for sustainable technology and chemical synthesis. Overall, organometallic chemistry remains a cornerstone of chemical innovation, driving progress in both industry and research.